record, so that's why the microphone's important. Is that good? Yeah. All right. Thanks for inviting me. And it's great to be out of Pittsburgh for a day. The it's really beautiful here. We don't have many alligators in Pittsburgh. Um, so the main thing I'm going to try and talk about is just show you both the resources we developed. We're always looking for collaborators, especially schools that are willing to work with us to develop materials and test them. Um, and I'll also try and throw in a little bit about what we've learned about learning. This is the people I've worked most closely with at our site, and Gail Harding, Jim Greeno, or actually psychology type people at Pitt that I've learned a lot from. So there's 3 different projects, places you can find our things packaged in different ways. The Chem Collective is our main site, and almost everything we have is available there. We recently started working on, we were initially aimed at college level classes. We recently started working on developing high school materials, and we have 8 fully developed modules. So if you're from the high school, that would be awesome to use those. And we set up studies to learn how things work in classrooms through this collaborative center that brings together many domains in cognitive science, trying to figure out what happens when you put things in the field. So our main sets of activities is a virtual lab is the thing that we're most known for. That's our most popular resource, and we have about 100 different activities ranging from high school chemistry up through AP and college chemistry. They use that virtual lab. For places where we either find that there's a real need for online materials for students, like stoichiometry, or places where we've discovered ways to teach things that we think are different and better, we have tutorials up online. And then we've also done some chemistry in context. So I just want to set up what's our philosophy of learning that influences what we develop. And for me, one of the most interesting early results in science learning was the course concept inventory result in physics. How many people know about this? Yeah, this is it's both interesting, and it was an interesting social phenomenon. So let me just say what it was first. Someone created a set of qualitative questions in physics, and this is what they look like. So I'm spinning a thing over my head, and at the point P, I let go. What happens? And then there's some that are like balls rolling off platforms, and it does the Bugs Bunny thing of goes over, and then it looks down and falls straight down versus other. And so this exam was given in classes as a pre and post study on people taking college students taking freshman chemistry. No improvement at all in the performance on the inventory, and replicated now at every level of school, most countries in the world. So Harvard was one of the ones that made it most famous. By the Harvard person saw this at a talk and said, "Give that to me. I'll take it to my students. I'll show you." And if he had asked them calculate the vector velocity 4 seconds after the guy released, they could do it, but they were learning how to do the math. And learning math does not mean learning concepts. That was the main take-home message. The fact that it was measurable, in physics, people love to measure things. It really got people's attention and got people really interested in education. It was great. And I think the take-home message was that students learn what you ask them to do. They don't learn all these extra things you think you're teaching them. That they learn the tasks you're giving them. So you better design the tasks so that the tasks reflect what you want them to know. So that's why we got into designing tasks that we think promote conceptual learning in chemistry. So what is chemistry? And the thing that makes it hard is that there's a famous paper, Johnstone Triangle. You really have to be thinking at 3 levels all at the same time. You've got what you can see in the laboratory. You've got something you can only imagine happening at the atomic level. And you have symbolic notations we've developed to understand things. And connecting these representations together is very difficult. So the first thing we went after was the sort of macroscopic observations and tasks that would really help students understand how to design and interpret experiments. So let me just show you this piece of software. So there's chemical solutions on this side, and you can bring them out onto the workbench. There's all sorts of glassware. So it was designed intentionally to be like a freshman chemistry lab. The chemistry is also freshman chemistry. So it's not totally accurate, but it's exactly the way we teach them chemistry works. Bring out a base. Yeah, you can. Yeah, nothing explodes. I know everyone always wants an explosion. It's not true that all chemists want to blow things up. Only most. Okay. So we've been working on the interface for quite a while, and some of the features of that are like here. I'm going to use sort of proper glassware for this titration technique. But I don't really have to in this mode because say I wanted to pour 0.01 milliliters of water between these two. The interface lets me do it. And sometimes that's fine because you want them to think about the chemistry concepts, not how you would do it in the lab. If you care about lab technique, then we switch this over to realistic transfer. It's based on the way video games often do these things. So the longer you hold this down, the more you pour. So that, I wouldn't be able to pour accurately, but if I use a burette, then I can pour accurately. Over here is a list of things in the solution, and this is the connection between the macroscopic and the symbolic. The one thing we're working on in other contexts, but we haven't put into the lab, is the particulate level. So of the 3 corners of the triangle, we have the symbolic connected to the macroscopic. The particulate is much more difficult because this thing is here in 10 to the minus 16th concentration, which means there's not enough pixels on the screen to show how the ratio. So it's a little bit complicated, and we've gone with separate simulations for that. And so we've created a lot of activities around this so that we get a sense for how the software works. And I'll go back to what we do with it for learning. So first, how do people use it? Our intent was that it would be homework. We really think that the end of the chapter problems in chemistry are not great. They are the things for chemistry that the physics problems were that led to the force concept inventory docking people. And so we really wanted students to design and carry out their own experiments as homework, and we get a lot of use that way. This is the use that we didn't anticipate. People are sick, they don't do a lab, and so you need to do a lab makeup. Lots of places use us for that. Pre and post lab, I think, is also a great use too. One of the few things I think in education that almost always shows a good effect in learning studies is if you prepare people for the physical lab by having them do something online that, like the lab, they learn a lot more. I think the open question is whether it's better as pre and post. It seems like pre would be better, but post has this advantage that they see the physical laboratory, and then when they do the online, they sort of know what it's about. And the really good controlled studies on that are yet to come, but early results suggest that post might be better than pre for laboratories. For the chemists in the audience, these are the topics we cover. We can't do kinetics. So the simulation is general, but it doesn't have time-dependent phenomena. And that's, if I could write the general time-dependent phenomena, I would sell it and retire, and it wouldn't be interesting. Yeah. But it would be so hard, and it would be so useful for industry. Its secondary use would be education. So this is, but it covers almost everything you do that involves wet chemistry in the high school and college curriculum. We're a community, and I'm putting this up mostly to show that we've had contributions from many different groups. We've had the lab translated into, I think we're up to about 17 languages now. We're up to about 250,000 students running experiments run online every year. So it gets a lot of use. You can feel confident that if you're using it in your classroom, it's stable. Support is difficult. So we intentionally went with an interface that was flexible because we wanted kids to design and carry out their own experiments. The problem with that is, what if they don't know what to do? So we're still working on help systems. This is the style that we have up now, which is there'll be a web page that shows them the activity, and they can get help. And we've made those hints a little bit dependent on what they've done in the lab in some cases. So we can know if they haven't done anything yet, they'll get a hint that's fairly, why don't you try pulling. If they have the right stuff on the workbench, then we'll give them hints based on that. So we can somewhat tell where they are, but I think that's one of the harder problems the whole field of online learning has to address. So we both provide a flexible environment to learn in and support at the same time. We give feedback, so if they make an error. We look for common errors, so in cases where we know from log files that they make these errors, we put in hints. This slide is a little bit of a shifting gears. Why is this useful? And let me just show two problems. This is a problem. You want to figure out what the heat of a reaction is. Heat of reaction is these things react, they give off heat. So the textbook would do this, tell you the experiment. This was mixed with that. The temperature went up. It's not a hard experiment. You want to know how much heat things give off. Mix them together, measure the change in temperature. So we really didn't think that this would be that hard, but totally blank stares, Carnegie Mellon students. And why is that? So we did lots of observations. What we discovered is how good students are at means ends analysis for problems. They write down the givens. They write down they know what chapter we're in. It's only 5 equations in the chapter, right? So you've got a bunch of numbers, you've got a bunch of equations. All meaning to the symbols is lost. It becomes symbol matching, you get to the answer. We find this over and over again. Even things simple as dilution problems with students who got 790 on the math SAT. They do the problem, they get to the end, and they're supposed to use that to go do the experiment. It takes them longer to remember what they were doing. Oh, they got the answer. What does the answer mean again? They have to go back and look at the whole thing all over again. So that's really where I think these environments, for chemistry, this is, I think, the analog to the physics one of conceptual learning. In chemistry, they can do the math, but they're not learning from the math what you think they're learning. Here's another one. This is from observations. We've discovered an interesting error we didn't anticipate. So this was a problem, figure out the reaction. So you're giving A, B, C, and D. You have to figure out how things react. Most students will eventually start mixing together all possible pairs. I'll mix A with B, then anything happen, I'll mix A with C. So here's an experiment where they mixed A with C. After they mixed it, they had this left over. And this is what's really happening. I mix equal amounts of A and C, so 3 A's and 3 C's. The rule for the reaction is that I can take away 1 A and 2 C's and replace it with a B and a D. And then I do that again. So now take away 1 A and 2 C's, replace it with a B and a D. And now all the C's gone, so the reaction is over. That's why there's A, B, and D left. More than 50% of students actually will write that the reaction was A and C goes to A, B, and D, which is not crazy because look what I wrote up here. A and C went to A, B, and D. The chemical reaction is actually a very strange thing. It's not a time. It's not this was there at time 0 and this is there at time infinity. This is a rule that gets applied to a collection of molecules. And once we realized the students didn't have that in their head, a whole bunch of errors students started to make sense. They're not thinking in this way. So we've created instruction. This is one of the cases where once we knew this, we created instruction online to sort of get out the word that this is something you have to teach your students. It's not hard. This diagram pretty much does it for kids. So there it is. And this progressive reaction is one of the most central ideas in chemistry, not emphasized in current instruction. That led me to my tutorial. So if you have students that are falling behind, we created a full online course in stoichiometry. It's also available broken up into tutorials because we think that kids struggling in freshman chemistry is because they don't have a good grounding in stoichiometry. Tutorials and very scaffolded problems. They're essentially worked examples in that if you press the hint button enough, it walks you through the whole problem. But we make it so that they hopefully are trying to do the problem as they do that. And then for new styles of instruction, we also have tutorials like these. For the chemist, here's everything that's covered in the stoichiometry course. I think it actually goes up into things that you probably cover in the college course. in addition to all the things that are from high school. It's also set in what we hope is an interesting context, that arsenic poisoning in Bangladesh. Why is it so hard to measure arsenic? Turns out the World Health Organization standard for what's safe arsenic in water isn't based on what's safe, it's based on what's detectable. Here's what the tutors look like. So they would walk you through step by step. This is actually a fallback. So if they can, first ask them to put in the real answer to the problem. If they can't do the problem right out, it does a walkthrough step by step of the problem. The equilibrium instruction, one of the things that progressive reaction, we set it in human respiration, because equilibrium is really about reactions that sort of flip from one side to another. And breathing is a great example of that. So in your lungs, you pick up oxygen. In the muscles, you release the oxygen. And we've set the entire equilibrium instruction in that context. This is how many, there's probably not enough chemists for this to be worthwhile. But it's sort of interesting. This is probably the most successful. Usually when you do a controlled study in a classroom, if you get like a 10% increase in learning, you're all excited. It's really, really hard to get a measurable increase in learning. This produced more than a factor of 2. And what it did was, to an expert, this is the way we solve equilibrium problems. And it's very algebra-based. So there's something in here that you can distill out of what's the real concept. And you can write this over again in a much more intuitive way that doesn't do the algebra. The algebra was only getting in the way of the concept. By rewriting this process and removing the x, we more than doubled student performance on difficult problems. So math and the way you present math, I don't think it's that it's a math skill that they're lacking. These are Carnegie Mellon. This is a study at Carnegie Mellon. It's that math doesn't give them the concept in the way that you can. So if you have something that students are struggling with and you're saying, oh, it's because they're weak in math, it might not be them. It might be that the math is obscuring the real nature of the problem. So this is a push of some materials for high school. So the conceptual learning-wise, we have a murder mystery, mixed reception, that is really, it's fun. It was done with the drama department at Carnegie Mellon, which is a top-ranked drama department. So the acting is a little bit campy, but the kids like it. It gets now about 50,000 plays a year. And it's a one to two class period activity, and it's clever chemistry, I think. And the star, the murder victim, is now a successful actor. He was nominated for a Tony for Book of Mormon. Yeah, we were his first paying job, I think. And then this is the latest project we did, funded by the Department of Education. And we took the chemistry standards. Actually, this was an interesting story for this group. That we initially took the chemistry standards as written for the state of California. And we created a mock-up of the first 4 activities. And then we ran them. We went through the process of showing them to the teachers and doing all the things you do before you really develop. And we were way off. Because what's written in the standards and what's on the assessment exam in California, there's just almost no overlap. So we learned you have to take all of the past year's assessment exams and look at them and say, what do they really need to know to do well on this exam? And actually, the exams were infinitely better than the written document. Like, look at what was on the exam. It's like, oh, this is actually pretty reasonable. The written document, I looked at and said, these people are nuts. They copied the table of contents from a college textbook and called that the California State Standards. It was really embarrassing for California, personally. But apparently the people in the room writing the exam are reasonable people. So the exam was really quite good. And we came up with activities that really target, put the chemistry in context and really target exactly what students need to know. I think Common Core will be an improvement, personally. This is just an example of this is one where we've used particulate representations to try and give a sense of stoichiometry. This is figuring out, like, setting in the context of oil spills and activating oil spills so that bacteria can eat them. And we asked them to figure out how many surfactants it takes to surround each part. This is our murder mystery. This one I want to close. This one is one that we've only run twice at Carnegie Mellon, and we're looking for places to use the material and participate. It's a pretty cool thing, because one of the things I think that's been lacking, at least in our approach to online learning, is we viewed it as human-computer, and that's it. So the computer interacting with the person, rather than the computer helping a group of students interact. Came out of the Language Technology Center at Carnegie Mellon. And what we're doing is we're putting students into a chat room, but we're going to put a computer agent in there with them to help guide the discussion. And we did a jigsaw design. The high school people probably do jigsaw. So you train students in different areas, and that's one way to have the discussion to sort of force engagement among students. So here it was the nature of weak forces between molecules, and there's 3 types of forces that are really quite different, and what you need to know for each is quite different. So they get online training. Each student is trained in only one of these, and then they enter into a chat room. And the chat room gives them data with one missing value. It's boiling points, because boiling points is the most natural outcome of the forces. And they're asked to, as a group, come up with a decision on what they think. Will it be higher, lower, or in the middle of the other 2 values? The sequence is such that the first one is one that one of the people was trained in, and the next one is. Then it goes into ones that mix. So one force, if you only think in terms of one force, it might argue in one direction. If you think in terms of another force, it argues in another. We're trying to get the students to engage with each other and say, oh, I think it should go this way. And the agent is Quinn. So you can see here's a discussion with the names changed, but real discussion. And the agent does a number of things. One thing, it guides the discussion. So it posts what they're supposed to be talking about. When they all agree on a result, they say ready. When everyone said ready, it moves on, shows them the answer. And it moves on to the next set of activities. In addition, we have some great transcripts where the students actually start arguing about whether Quinn's a real person. Because at the time we were doing what we call Wizard of Oz studies, so in order for one of the conditions was that the tutor would be a real person. So I think the students knew that some people had a real person in their chat room and some people had a computer, and the computer was good enough that it actually fooled them. So here's some of the main thing it does is it has a set of things that experts would say about the activity, and if the match between what a student said and what the and one of these things, it revoices it. So we'll say, Joe will say something like, I think it's going to boil higher because it has a dipole, and then the agent will say, Joe, are you saying that molecules are large dipoles? The other thing it does is what's called accountable talk moves, which are, if someone's being quiet, it will ask them whether they agree or try and get them involved in the discussion. And so if you want to sort of help, want to participate in that kind of study, they've developed things for chemistry with us, and they have a biology group. They've done biology things. So either of those 2 fields, if that looks interesting to you, please let me know. And we also develop, so we have 100 virtual lab activities, only about 30 of which were our idea. So most of what we do is developed for some school or some group that really wants something purpose. So if you have anything that you'd like a virtual lab for, please let us know. And if you're interested in participating in learning. So it's been a large group over the years, and we have lots of people to thank for keeping us going. Thank you.
We do have time for questions.
Oh. We actually, we did random. Yeah, sometimes that's an interesting debate of what should you do. The system is set up now. At the time we have all the real data from. Oh yeah, I should say that the data shows they learned from it quite well. We had them all in a room together, so we would know what was happening. We knew they were in a room with someone else, but they weren't sitting there. Now there's a chat room, a lobby, and when you enter the lobby, as soon as there's 3 people in the lobby, it just so if students wanted to work together, they could just enter the lobby. Whether you should allow. There's also a really interesting study going on at Berkeley now about how to group students by ability. There's been this belief that you should create diverse groups, but it's not clear watching transcripts of interactions that 3 low students together is not the best choice. Interactions when you put 3 low-performing students in a group, so far it's looking like they're much richer. Yeah, it's in the sense of students feeling that they're like. There's one transcript where one student says, like, no one's saying anything, and then one student says, "Oh, I have no idea what's going on," and the other person says, "Oh, I'm so glad you said that. I have no idea what's going on." And Berkeley, it's a great, for this kind of thing, Berkeley is a great environment because there's a rule in California that the best student from every high school immediately gets admission to Berkeley. So the incoming class at Berkeley is much more diverse background-wise than you would think. Yeah, we've been pushed, Hewlett Foundation especially, that funding source was pushing towards courses, and we always push back against that. We think resources, everything's very bite-sized. Oh, I'm sorry. Yeah, if you go to the Chem Collective website, or yeah, but yeah, that's probably the easiest way because then it goes both to me and my curriculum head of curriculum, and he's good at responding, and I'm not so good. Oh, that one, it's currently set up. At the time we did the study, we were just physically in the room with them. So a lot of the early, especially if you've never run it with students before, we try and always do it in person with them because then we can help and see what happens. Based on that, we've created the online versions they create a random sample, so they can't just look at what their neighbor. They're allowed to try as many times as they want, so if they get it wrong, they have to reload the page and they get a new random sample. Try until you succeed. Feedback is still a little weak. We're working with a group from Israel on analyzing mouse click level data to figure out strategies. And we actually have succeeded in wanting to figure out what's reacting with what. We've discovered 3 main strategies students use, and based on that, we'll be able to know what they're trying to do and give them appropriate feedback. We initially spent a lot of time building in the functionality we need for saving, and then it turns out it's not that useful, so we turned it off. We're now porting it to HTML5. We're going to bring it back, but most of the activities, it's not like once you know what you're doing, there's a lot of work involved. And so there's only 1 or 2 things they need to do. In the high school activity, where that one's set up as a real many pages, so maybe 20 pages that you go through, it saves state, and when they come back, it puts them on the page. Yeah, and so one of the advantages, especially as a pre-lab, it's very hard to get students to design their own experiment open-ended, both safety, but even without safety, there's time issues. And here, like a log of the unknown reaction one, I bet it's about 5 experiments a minute. Very, very fast. For kids, adults slower. Training too, like training teachers how to use the virtual lab, 10 minutes. Training students how to use it, 3. Oh yeah. Yeah, going there because we were doing it with them in person. Well, actually, we've done it since then. Yeah, completion. So in the in-person one, it was just if you came and participated, then you got credit. It is, yeah. So we definitely do not put high stakes on our. It would be interesting to think of what these things would mean in a high stakes setting. Oh, participation is 10 points, and if you look enough, and so I think you have to do a little bit of looking at the log to see if they at least think you're looking at the log. But for the most part, the other way to do it, I think, is that I do with the virtual labs, because there we assign it, and they can pay someone to do it for them. We put questions on the exam based on the labs. High stakes test them on what they should have learned. Oh, detailed meaning. Yeah. I'd like to see that. I'd like to know that study because that's the only one I've heard of where there's no. So the stuff in the 80s, like so when computers first became available, there were lots of studies, and it led to this phrase called cognitive noise, which was that it was interesting. If you gave students who had done the physical lab, versus students who had done the virtual and physical. 6 months later, the people who had done only the physical lab couldn't remember anything about the ball, except maybe the social context. They'd go, oh, that was the one that had all the little balls. You know? And seriously, and the ones who had done the virtual lab actually could remember, oh yeah, that's where we were trying to figure out what ion was in it. And then further studies made it, there were just too many things happening in the physical lab that they couldn't think about the context. You have to do a really bad design. I've never heard of a pre-lab not helping. So I like to see it because it might be interesting to look at it and say, what did they do different from these other studies that succeeded? Yeah, and that's actually Bob Belford from University of Arkansas Little Rock has done a lot of if it's pre. What he does is they've done the thing in the physical lab, so now they sort of have the goal and what it really looks like in person, and then he has them do more design activities. So it's not a replication; it's actually building on what they did in the physical lab. And we have not done enough of that, that's for sure. The one thing we have when in acid-base chemistry, because we spend a lot of time on it, but if you look at what they need to know for organic and biochem, there's almost only two ideas. One, buffers exist. Two, I like we did this one pretty seriously. So we interviewed biology faculty and chemistry faculty. Went up to a chemistry, like a biochem lab. Say, how you design your buffers? Like, what do you mean how you design? Like, when you need a 6.8 pH buffer, what do you do? Like, there's the shelf. It's like powder 6.8, 6. You take the 6.8 powder and you're dumping it. And but yet we spend weeks on, like really a week on that, maybe students actually, because it's one of the things that is hard, and so they really study that. And the one thing they really need to know is every proton has a pKa associated. It's a proton that can be there or not. It's got a pKa, and the pH is above that, the proton's gone, and if it's below that, it's there. If you know that, you know everything you need for your course. I dare you to find it in a freshman chemistry book. The one thing they need to know, we don't even teach them. So I think the alignment problems are severe. There's being an attempt at College Board, so the AP courses are being redesigned. And at the same time, they did this Pathways to Success document where they come up with what you should do in middle school. And it's actually, I think, fairly nice. Melanie Cooper was the chemist. For that level of alignment, there's some work. Oh, yeah, I mean, I think it's the fundamental challenge of science ed, actually. I don't know if anyone has a solution, but I think tasks that we're good at creating tasks where those strategies, memorization, means ends analysis, aren't enough. So we're forcing students to do something, but whether we're providing them the support they need to succeed, that I think is harder. I don't know exactly. I think that's the fundamental challenge of science education. The movements like Common Core and the AP redesign have this idea that there's a science practices dimension, that students should know how to create and interpret representations, trying to build at least that level of skill and support for those skills in. But I think the jury's out on whether that's appropriate scaffolding, or it's going to be really hard. Discussion groups, I think discussion groups with students working on very hard problems, the only thing that anyone has. Create interesting tasks and get groups of students to. But who knows? Yeah, I mean, it's hard. 19. Wow. There are numbers there. I just noticed it. Great. Oh. So this, I can send you the paper on this. This is I didn't do it because it's sort of very detailed chemistry, but yeah. Let me go a little bit further. This is a little more an extension of this. No, that's a general. This is actually one of the biggest problems I think in instruction is what's called the expert blind spot in cognitive science, which is that experts don't. So much of your processing is subconscious and intuitive that you don't even know what you're doing, and exposing that can only be done through student data. Probably. We've done something that's quite interesting, which is we bring in psychologists and we teach them chemistry. They're like, wait, how do you expect anyone to know that? It's quite interesting. But one of the things that's been common across all fields, so in geometry, it was that when people are doing a proof, they actually create a sub-goal structure in their head before they write down the first action. All the student sees is the first action, and they don't vocalize the sub-goal structure they're creating. Statistics, it was, and so if you build that into the instruction, you get significant learning gains. Statistics, it was that we teach them how to do procedures, but not when to do them. In chemistry, we discovered this interesting thing that in equilibrium problem solving, you actually you have to select a reaction you're paying attention to. So I'm mixing acid with a base or something. I first do one reaction, and then I start looking at other reactions. And the criteria you use to select the reaction you're looking at is, most people probably don't even know why they're doing it. They just know it's the right. We've figured out what you're really doing and teaching students. I think that's one of the biggies. I think looking for things that they need to know that you aren't going to give to you don't even know you have to tell them. Well, thanks everyone.